Hello, thank you for joining me in this Memfault webinar. Today, we'll go through a complete integration process for an ESP32 project. We'll start from an existing open source project that is really useful as a lot of code, but does not offer great observability. We'll add the Memfault SDK, report some metrics to Memfault, show how you can capture what we call device vitals, so indicators of how well the device is performing, and then how you can capture your own metrics that make sense to your specific project. We'll show how to collect core dumps, capture some crashes, debug them inside Memfault, and all of this should take us about 30 minutes. So without further ado, let's get started. My name is Thomas Orlandi. I'm the field CTO of Memfault, and I spend most of my time working with our customers on integrating Memfault inside their product. If you want to chat more, feel free to reach out. We're always happy to discuss what's the best way to observe your devices. Our mission at Memfault is to make software the most reliable part of IoT. We think there's no reason for devices to malfunction because of software bugs. The only valid reason for a hardware product to malfunction is when it's physically broken, when there's a hardware issue. And so we give you tools to monitor your fleet of devices, analyze how they're doing, make sure that from one software version to another, the quality of the software improves, debug issues when they happen in the field, find ways to understand the bugs, reproduce them, and fix them quickly. And finally, we offer an OTA delivery system so you can ship updated software to your customers quickly and test it as you deploy it to catch potential problems before they become too wide. This is our mission, and today is just a quick example of how you can do this on a microcontroller-based device. Memfault supports all sorts of IoT devices, including microcontroller working with Zephyr OS or FreeRTOS or bare metal. We support Linux-based devices and Android-based devices as well. Make sure to reach out for more details. This is going to be a pretty technical presentation, so I promise to stop with the slide really soon and jump right in. But before I do, I want to tell you a little bit about this project we're going to be working with today, because I'm pretty excited about that. It's an open source project I've been following for a few years now. I've been using it myself, and it's just a really cool example of what you can do with an ESP32, a very low-cost device, obviously, and a good amount of open source and some fancy modern technology, including neural networks, and implemented here with TensorFlow Lite. The name of this project is AI on the Edge device. It's kind of a mouthful, and you can find it on GitHub. It runs on an ESP32 camera module, which you can buy for less than $10. And the idea is that it takes a picture of your utility meter, can be water, gas, electricity, every minute, converts all the digits of the meter into an image, runs them through neural networks to convert that into a number, and it's able to report via MQTT or to a local HTTP server what is the current reading of your meter. And so with that, you can easily monitor your gas consumption, in my case, see how much gas is being used at any point in time during the day, and transform a dumb meter into a smart meter. I love that project. I think it's really cool. I haven't seen it crash too much, but that doesn't mean we don't need observability. And so today what we'll do is take the open source version of AI on the Edge, check it out on my computer, add Memfault SDK to it, and see how much effort is required to start observing an IoT product. At the end of this presentation, we'll look at the Memfault dashboard with data from this device. So I've already done this a few days ago, and we'll look at the stability of the device measured by Memfault. And in this case, spoiler alert, I've inserted a bug to make sure it would crash a little bit more often than by default. And we'll also look at some custom metrics that I've decided to add and show what they look like in Memfault dashboard. So we'll go from no visibility at all to the device to a good understanding of how well this device is performing in the field. In addition, we'll look at other tools provided by Memfault, including zooming on one device or zooming on one specific bug to understand when something goes wrong. This specific project uses the ESP32 framework, and it's built with Platform.io. Platform.io is an open source build system. It's just an alternative, or maybe a wrapper would be more accurate, around CMake. So a little bit of the conversation today will be specific to Platform.io. I'll be following this guide from our website, but what I wanted to show here is that we have guides for all sorts of platforms and integration. And so if your project is not using Platform.io, or if you're not even using ESP-IDF, but you're using a Nordic microcontroller or a Dialog microcontroller, just head over to our website and see if you can find a guide that will work for your specific setup. And if not, make sure to reach out. We'd be happy to help. We support a lot of microcontroller combinations. Okay, so what is this integration? What does it include? And these steps are pretty much the same on any microcontroller, any operating system. Will follow the same principles. The first thing we'll want to do is add the Memfault SDK source code to our project. So we'll just check out the open source project first, and then check out the Memfault SDK. It's also open source, and add it inside the project. Then we'll want to make sure our build system is building the Memfault SDK source file. So we'll do a little bit of a CMake configuration to point it to the Memfault source code. With the Memfault SDK for ESP-IDF, we add a number of configuration options directly into the ESP-IDF component system. So we'll need to configure ESP-IDF to configure Memfault, and that will be our next step. Then we need to edit our source code a little bit. We've added the code, it compiles, but we need to make sure Memfault is now running and used. The first step will be initializing the Memfault SDK. Second step will be making sure that we capture the data we care about and push it to the Memfault SDK. And then finally, at regular interval and in a thread that we choose, we'll need to tell Memfault to take all the data that it has collected and upload it to the cloud. So we'll see how to do that in that last chapter of our integration, publishing Memfault data to the cloud. First thing I want to do is check out this open source project. So let's clone the project. As you can see, we're really starting from scratch today. And once I have checked out the project, I want to make sure I also check out all the submodules that are used by this project. That includes some libraries for the ESP32 camera, the TensorFlow Lite runtime, those kind of things. Okay, at this point, I could just compile the project. If I go into the code folder, I can see it's a standard Platform.io project. It has a platform.io.ini file, and the main folder has a lot of source code. Let's fire up an IDE to do a little bit more work here. So I have my project. I can see all the source code in main in the main folder. So that's the main project, with the main CPP being the entry point here. We have a CMake file, and then a lot of the code, the interesting code if you're looking at this project, is actually in the components folder, where you have a lot of different components. And some of them, including the flow control, is probably the most interesting one. It's running its own thread to do the image recognition at regular interval and push the result via some other component. So now that we have the project checked out, we want to add Memfault inside this project. So I'll go back to my terminal here, and I'm going to clone the Memfault SDK as one more component in the project. Done. And then I need to make sure It's here. Done. It's here. And now I need to make sure Platform.io builds it. And the easiest way to do that here is to open the CMake list file, where we already have a bunch of CMake configuration for this project. And I'm just going to declare one more component. So that will build the Memfault firmware SDK using the memfault.cmake file from our ESP32 ports inside the Memfault firmware SDK. Good. We need to do a little bit more configuration in platform.io.ini. So here we want to tell the Memfault SDK that it's building inside Platform.io. And so that's the Platform.io enabled equal true argument. And if you want to follow along at home, you can just look at our reference documentation here, this page that I pointed out earlier, which has all those steps. So you can just follow all those steps. This is same thing that what I'm doing here. Then we want to add some build flags. Specifically, we'll start with a number of includes. We want to include the main/memfault folder, so it doesn't exist yet. Let's create it. And this is where we'll put any configuration to Memfault that's specific to our project. We want to include components, Memfault firmware SDK components include, so it's just the primary include folder for the Memfault SDK with a lot of header files that are available in there. So we want that to be available on the search path. And then we want to always include the FreeRTOS trace.h file that we provide because this will make capturing a core dump possible. So that's also detailed in our instruction manual. With that, we also need to give the linker some information. Part of the magic of Memfault is that we're able to capture crashes and core dumps, notice when you're rebooting, why you're rebooting, detecting reboots that are not expected. And the way we do this is by storing some information in regions of RAM that are not overwritten when you restart the device. So to make that possible, we use a little bit of linker magic. If you're building inside the ESP IDF, the linker magic is implemented through what's called linker fragments. It's a concept that's explained in the ESP IDF programming guide. And so here, the linker fragment file is part of the Memfault SDK. We just need to tell Platform.io that we want to use this. So that's what I'm doing here. And then finally, Memfault uses unique identifier for each firmware image. That's how we can map the data that we receive from your device to the symbol so that we know what metrics are being updated, what version of the firmware crashed, this kind of thing. And to include a unique build ID in your project, we provide a tool. And this tool, we need to call it every time we do a build. You could do that manually, but it's going to be tedious. So we just have this little add buildid.py script that will do that for us. And so I'm just going to add this add buildid.py. I'm going to move it to the parent folder here. Bear with me. Here it is. And this add build ID, this is just a little bit of Platform.io magic. Every time we make a new firmware image, so elf file, it will call the firmware build ID.py script that's included in the SDK that just generates and adds a build ID inside the firmware image. Okay, and with that, we've done the configuration. This is by far the hardest part of this process. Inside the Memfault folder, we do need an empty configuration file, even if we're not setting any option at this time. So I'm going to create this memfault platform config.h here, and I'm going to leave it empty for now. Okay. So now everything is ready. There's a few more things we need to do, though. We need to make sure we configure the SDK, and then we'll need to make sure that we actually use it. So to configure it, I'm going to reopen my terminal. I'm going to use the pio command, which is provided by platform.io. So if it's not available, you can do platform.io pm activate, bin activate. And so now you can do pio run. The environment is ESP32 cam, and the target is menu config. Okay, so once we're in menu config, we'll want to configure a few options that are important to Memfault. To look for options, you want to use the / key on your keyboard and then type the keyword you're looking for. So here I'm going to start looking for core, and I'm looking for an option called save core dump to flash. So ESP core dump enable to flash here. I'm going to turn that one on. The other option that's important, really important to Memfault, is setting the project key. So every project in Memfault has a project key. We'll need to set that here. To find the project key, you're gonna go into the Memfault app, grab the project key here in the top right, copy it, and just paste it here inside menu config. And finally, we need a third option to turn on HTTPS. So by default, the HTTPS client is not included in ESP IDF. We needed to talk to Memfault, not the server though. HTTPS client enable, yes. Okay. And I believe that's it. So with those options, the ESP framework is configured. I'm going to save that. Quit. Okay, perfect. And then we want to add a partition to save the core dump. So I'm going to define one more partition on the flash. Here we have enough space to store the core dump in a separate partition, so we'll do that. The type of the partition here is going to be data. The subtype is going to be core dump, and we're going to set it to be 128 kilobytes. Save that, and Memfault is configured. And so now we just need to make sure we activate it, that we initialize Memfault, and then that we push data to Memfault. To initialize Memfault, I'm going to open the main.cpp file in the main folder here. And I'm just going to add a call to initialize Memfault. So first step is going to be including the right header, which is Memfault ESP port core.h. And then we want to call the Memfault boot function. And that function we're going to call here from the app main function. So the app main is the main entry point of our firmware. In this project, the app main function spawns a number of other tasks that run in the background, and then it just returns, and the other thread keep on running. So here at the end of the app main function, I'm going to call memfault underscore boot, and I will just initialize memfault. Next step we wanted to cover is how to push and capture relevant metrics. So first capture relevant metrics, and then we'll talk about publishing the data. To capture relevant metrics, we need to do two things. First, we're going to define what are the metrics we're interested in capturing, and then we're going to actually provide the value of those metrics to Memfault. So to declare a new metric, we're going to go into the Memfault folder here inside our project, and we're going to create another configuration file that's whose name is predefined by Memfault, and so that's Memfault metrics heartbeat config.def, DEF. And that file should include a call to sdkconfig.h and then a few calls to the macro memfault metrics key define. And here we're going to define a CPU temperature metric. It's going to be a signed metric in the Memfault SDK. And we're going to have 3 metrics like that. The second one is going to be the Wi-Fi RSSI. And finally, we're going to save the time it takes to process an image as a third metric. Okay. Now we need to provide a value for those metrics. So what we've done here is tell the Memfault SDK that we are going to be capturing those values. So we're going to assign a unique ID to each of those metrics. We're going to reserve some space in memory to store those metrics. Now we need to actually provide the value for those metrics. So to do that, I'm going to open another really interesting file, which is the main flow control.cpp. It's in one of the components that come with the project, and it's really where all the magic of the image recognition is happening here. This file is pretty huge. The function we really care about here is task auto do flow, and so that's the function that's the task that's running continuously, slipping in between each recognition, but that's where all the recognition is happening. So while it's running, it's going to do this. And I noticed when I was looking at the output in the logs that it was already outputting all the information that I'm interested in. So that's why I found where the information was generated, and I'm just going to come here and add my Memfault logic in here. And so in here, to push the data, we're going to use the Memfault metric set signed macro. And here we're going to pass the recognition time seconds, which is going to be the get uptime minus the time that we started doing the recognition. So same thing as what we have here in this log. So I'm just copying that. And then I'm going to do the same thing for the CPU and Wi-Fi, which is I'm just going to copy what's done in the log line above. So that's going to be temperature read. Obviously don't need that anymore. And then here we want the Wi-Fi RSSI, and that is provided by the get Wi-Fi RSSI function. Okay. So you see we get a few indication from my IDE here that the symbols are undefined. There's a few reasons for that, but I'm missing a number of include is the main reason here. So we're gonna go up and add the Memfault metrics.h. Now that we're collecting the data, we need to make sure that regularly we tell Memfault to upload the data. Now, we don't do this automatically because we need a thread to be able to do that. And so in this configuration here with the ESP and platform IO, we don't want to start a thread automatically. So you need to use a thread for that, or to create your own thread, or add that to one of your existing threads. In this project, we have this app loop function, which is just used to initialize everything, and then it exits, it returns, it stops running. And so it's very simple to just use that. So I'm going to add a while loop that never returns. I'm going to add a log message, and we'll need to add some header for that to say that Memfault loop is running. And then we will call the Memfault ESP port HTTP client post data function, which will check to see if there's any Memfault data buffer locally. If there is, make an HTTP request using the ESP IDF HTTP client and check the return value. And if everything is good, we'll get a return value of 0. If it's not 0, we know something went wrong. And help me, Copilot. Yeah, Memfault post failed. Perfect. Whether it worked or not, we're going to sleep for 60 seconds. And then we'll, so that variable X delay was already defined above. Finally, one last piece I'm going to add to this project before we compile and flash our device is that I've noticed it doesn't quite crash a lot. And so for our demonstration, we're going to add, we're going to give the project a good reason to crash. So we're going to say if that counter, when that counter gets bigger, gets to more than 300, we will trigger an assert, and that will crash the device. And so that's just a way to make sure that at least every 5 hours we'll crash and reboot the device so that we have something to look at in the reports. Okay, so save. And now we're going to compile and flash the device. So let me grab my ESP32, plug it to my computer, and run that. Okay, so it's built. Now it's flashing my device. And now we're going to monitor the output. So you can see the app starting. It's going to do a lot of things. It's going to read the configuration file on the SD card to connect to my Wi-Fi network. And eventually, it's going to tell me that Memfault is being initialized, so that's good. And then it tried to push data to Memfault and succeeded, result 0. So now I should be able to see data flowing inside Memfault. Let's go check that. Going back to your project here, you can look at the integration hub to see data that was recently received. And so we can see we have data from this device just a few seconds ago. And if I look at the processing log, I can even see which device sent data, get the details of the data that was received, and that is a very useful page when you're debugging your integration. One thing I haven't done yet is upload the symbol files. So for Memfault to be able to analyze the data that is being received, including metrics and core dumps, we need to have the symbol file from the project. And ESP32. Now that we have this information pushed to Memfault, the integration is complete. And if we wait about 1 hour, we'll start seeing more data come in. And the reason for waiting 1 hour is because we haven't changed the default heartbeat configuration. So unless there's a crash, Memfault will only push metrics in that example every hour. But what I really want to show you is the device vitals. So here you can see the stability of the firmware over time. So you can see that in the version I had running so far, we had approximately a crash every 2 hours. So the median time between crash was 2 hours. And another way to say the same thing is that we had about 50% of crash-free hours. So that's something that Memfault will collect for you out of the box. You don't need to do anything. You'll get that metric. And then below, I've collected some other stats on how long it took to recognize images. So you can see it's about 38 seconds in my case. How hot the CPU gets while it's doing the work, and how the Wi-Fi change throughout the project. So here, if we wanted to debug exactly why is there a crash every 2 hours, what's the problem, what's crashing, I can go into the issue page, see that I have a number of errors that were reported by my device. The number one problem is this assert in the main function. And so here I can see that in the main.cpp at line 568, we're triggering this assert. So that's it. That's our integration. So we went from a project that is already existent, a significant amount of code, not a very Not a trivial example by any mean. We've added the Memfault SDK. We've configured the Memfault SDK with the ESP IDF. We've made sure to integrate into the build system to build the Memfault SDK. We configured a collection of metrics so that we could capture data that was also relevant to us. And so we have the device vitals plus some project-specific metric. And we've configured the upload of the data, in this case, via the ESP IDF HTTP client. And with that, we have a full integration of Memfault monitoring and debugging. I hope you found this at least instructive, maybe entertaining, and that you will reach out with follow-up questions. And thank you very much, and have a great day.